Okay. Okay, so like I was saying that due to the change in measurement instruments, this makes things seem as though everything is relative. And we'll go one step further to help magnify the awareness of this phenomenon. Okay, so we have our two twin spaceships. This one, of course, is moving across at our usual 260,000 kilometers per second. This one here is basically at rest. Doesn't have to be, but it makes it easier to understand. And therefore, it extends across 300,000 kilometers. And we'll put a clock here. We'll call this clock C. A clock at the other end, we'll call that clock D. A clock here at this end, call it clock A. And a clock at the other end, we'll call it clock B. Now, as you recall, this is shrunk down to 150,000 kilometers. And again, it's moving at 260. But let's move it back until B and C are lined up. So we're moving this back 150,000 kilometers. And let's say that B and C, both of the clocks say 12 o'clock. So they're synchronized. Then it moves over until A is lined up with C. So we've moved a complete distance of 150,000 kilometers and did so at that speed. So you divide that by 260 kps, 260,000 kps, tells you that it took a time period of 0.577 seconds for B to move from here to there. In other words, from B to move here to there, and therefore lining A with C. Therefore, since this clock is at rest, it would have indicated that a time period of 0.577 seconds had passed, just over half a second. However, Mr. B, as you recall, his clock is ticking at half speed, so he would measure half of that. So you divide that by 2, which equals approximately 0.288. But what about Mr. A? Well, his clock is ticking at half speed as well, but you recall Mr. A is ahead of Mr. B by 0.866. So to see what time his clock said when he's lined up with clock C, you have to add the offset. So plus 0.866, which gives you a total of 1.154 seconds. So what does all that mean? Well, when Mr. B was lined up with C, he noticed the clocks were synchronized, so he tells Mr. A that when I was lined up with clock C, both our clocks said 12 o'clock. And then he asked Mr. A, what time did your clock say when you lined up with Mr. C? And he says, my clock said 1.154 seconds after 12 o'clock noon. Let's say it's noon. However, he was very surprised to find that clock C indicated 0.577, which is 1/2 of this. So based upon their measurement instruments, they observed that this clock on the other twin spaceship seems to be ticking at half speed, because it only measured half as much as what Mr. A's clock seems to have measured. And they could do the same test with this clock, clock D, and they'd get the same results. So from their point of view, these clocks are ticking at half speed, which is kind of strange, because from this guy's point of view, these clocks appear to be ticking at half speed because they actually are. So his assessment is correct. Theirs is due to the change of the measurement instruments. So it appears as though these clocks, from their point of view, are ticking at half speed, even though they're not. Next, B started here at this end, but then let's say eventually he reaches the opposite end, lining up with D. Therefore, he's covered a complete distance of 300,000 kilometers and did so at a speed of 260,000 kilometers per second. Therefore, the time taken to complete that is 1.154 seconds. But from Mr. B's point of view, his clock is ticking at half speed, so you divide that by 2, which equals 0.577. So from his point of view, while traveling at this speed, it took him that long to cover this distance. Therefore, using that, he realizes all he has to do is multiply that times the time period, and that'll tell him exactly what distance he had crossed. KPS, and the outcome is 150,000 kilometers, 150,000 kilometers. So he's saying, what the heck? The other twin spaceship has shrunk to half length, and the clocks on the other spaceship are ticking at half speed. What's going on? Meanwhile, from his point of view, it's this spaceship which has shrunk to half length, and it's their clocks that are ticking at half speed. So, understanding how this happens, you realize that it's not just saying that everything is just relative. There's a reason behind it. Because if you say that everything is just relative, that means you're saying that it's okay to add magic into science. In other words, if everything's just relative, that means you're saying it just is, and there's no cause behind it. There's no sound foundation making it happen. But based upon what I've exposed to you and how the measurement instruments change, you realize there is a sound foundation. So you might say, well, how does he know that he's moving at 260,000 kilometers per second? Well, one thing they could do is, let's say when the two spaceships were both at rest and one takes off, what they did was calculate exactly how much fuel is required to get him up to the speed of 260,000 kilometers per second. So he comes around, then comes in this direction. By the time he's run out of fuel, then he's coasting. And so his constant motion now is in the direction of 260,000 kilometers per second across space. And there you go. And you'd say, well, I don't know, that's not really accurate. So let's assume that we don't know how fast we're going across space. Does that mean we're stuck as far as measurements go? And the answer is no. Imagine that this is a train, and I have an identical train, same length. And I have clocks at the ends, clock A and clock B. And let's say I put them, both trains, line them up together, and all clocks say 12 o'clock. Or I could take my train and put it over here, and again, all clocks say 12 o'clock. And then I could slowly move over until I'm lined up again. Let's say all clocks say 1 o'clock, so it took an hour. However, if my train was a little bit longer, it would take more time to line the rear ends up. If my train was twice as long, this would take an hour, and then it would take another hour for the rear ends to line up. And so based upon kindergarten math, you'd be able to realize, oh, my train's twice as long as that one. Now, when B went from here, like the front here, right, went from here to here, he measured that much of a time period. When the rear ends lined up, Mr. A measured this much, which is twice as much. Therefore, based upon that and kindergarten math, from his point of view, this spaceship is twice as long as this one is. And as you recall, they still think that this spaceship is 300,000 kilometers long because it seems to take 1 second for light to go from one end to the other. Or if they measure it with a wooden ruler, the wooden ruler shrunk to half length, so it still seems to be 300,000. So from their point of view, this one is half the length of this, right? Theirs is twice as long, so this is half the length. Therefore, it has to be 150,000 kilometers long. Now, based upon that, they realized they crossed a distance of 150,000 kilometers in this much of a time period. Therefore, you can simply take that 150,000 kilometers divided by 0.577, and they end up with a result of 260,000 kilometers per second. So he can calculate what his velocity is relative to this guy here. So again, anyways, point being, from either point of view, it always seems to be the other guy who's shrinking in length. It always seems to be the other guy whose clocks are slowing down, even though that's not necessarily the case. Now, to add to this confusing situation, imagine we take, again, we have our, let's say this is our 300,000 kilometer spaceship. And then there's another one going in this direction, Mr. Reference, and another one going in this direction. And we'll call this one A, this one B. So let's say that A is at rest in space. This one, Mr. Reference, is moving at the usual, 260,000 kilometers per second. Now, and these were all 300,000 kilometers long. So when A looks at Mr. Reference, he sees Mr. Reference has shrunk to half length and his clocks are ticking at half speed. But if he starts to catch up with Mr. Reference looks a little bit longer, his clocks are ticking faster. If he eventually catches up with him, then their rulers will be the same length and their clocks will be ticking at the same speed. But if he takes over and moves faster than Mr. Reference, let's say he's in the B position now, even though he shrunk to even smaller size than length, and the clocks are ticking even slower, because everything seems to be relative due to the change of measurement instruments, once again, Mr. Reference seems to have contracted in length and his clocks seem to be ticking slower, even though that's not the case at all. It's actually this guy whose clocks are ticking slower. So it doesn't matter if you're moving faster than Mr. Ref or if you're moving slower than Mr. Ref. Any form of relative motion gives you the same results. In either case, it appears as though it's the other guy who's getting shorter in length and clocks are ticking slower. So you can't tell as a result of that whether you're moving slower than him or faster than him. But that doesn't necessarily mean that it's neither one or the other. It's not just all relative. You are in one of those two positions. It's just there's no way that you can tell which position you're in. And so you can think of A and B as, well, that's another story. Let's put it this way. If these guys continued on these paths, there'd be a significant difference in the time passing. For instance, if this guy could experience maybe 1 year, this person over here could have experienced 7 years, this one maybe in between 3.5 or whatever. So there's a significant difference, but despite that, everything seems to be the same. If this guy's going just the right speed, this one will appear to be half length and clocks ticking at half speed as well, even though he's moving a heck of a lot faster than this guy is across space, because this guy's at complete rest. For this guy to be able to see him as half length, he has to be moving at 297,000 kilometers per second, pretty close to the speed of light. So there's a huge difference, and he's moving through time at 1/7 of the maximum speed possible. 1/7 the speed at which Mr. A would be moving through time. So anyways, but it all seems to be relative, even though it's not. Okay, so next what we'll do is take analysis of, or make an analysis of simultaneous events. Is there such thing as an absolute simultaneous event? And the answer is yes. But just because you can't detect whether you're measuring an absolute simultaneous event doesn't mean that such a thing cannot exist. Unless, again, you believe that everything can just happen without a cause. Okay, moving on.